Okay, so what this method does is the following. If you have a11 x1 plus a12 x2 equals b1, and a21 x1 plus a22 x2 equals b2. Okay, so just like Gauss elimination, it will use a11 as the pivot to eliminate a21. Use a11 as a pivot the same as Gauss elimination. So it will be a11 x1 plus a12 x2 equals b1. And then since we eliminated a21, we don't really have to write it down. We'll just have a22 prime, because a22 will change because you used a11, the first row, to eliminate a21. Okay, so far it's the same as Gauss elimination. The difference is this. What Gauss elimination will do is it will do two things. One is it will try to make a 1 as a pivot. Yeah, question?
Where did the A21x next to the A22x2 go? A21x1 on the lower left hand.
So we eliminated A21 to eliminate A21, just like we did for Gauss elimination. So this is just high level information on how this works. We'll get into the actual nitty-gritty soon. Okay. Okay, so it's similar to Gauss elimination here, but there's an extra step here. What it does is it tries to make all the pivot elements go to 1. So you could do that in one of the two ways. One is you could do it before, that is, you could divide the whole first row with divided by a11, in which case a11 will be 1, or you could do it afterwards. It doesn't really matter. So let's just say you do it afterwards. So this will become 1 because you divided by a11. Okay, the next step is that you will eliminate a12 divided by a11. So sorry, just did it this way. Use a22 prime, which is this element, to eliminate a12 divided by a11, okay, which is sitting here, right? So we want to eliminate this using a22 prime as a pivot. So what that will give me is x1 plus 0 equals, I'll write b1 double prime. The double prime is because this is the second iteration and not the first one. And then we have a22 prime, x2 equals b2 prime. And then, as I said, you also want to get rid of, you need to make it unity. So you divide it by a22 prime. So this thing will make it 1. Okay, so the final expression will be like this. x1 plus 0 equals b1 double prime, and x2 equals b2 prime, a22 prime. Okay, so what you see is you have the solution right here. So x1 is b11 prime, double prime, x2 is b21 prime, a22 prime, right? Just by construction, you did not have to do the back substitution. You just got it. Now, I said there are two things you need to do here. There was pivot equals 1. We need a 1. And then second step was elimination. Okay. What I've shown you here is I did the elimination first and did the pivoting, put the pivot as 1 after that. But normally the way they usually do this is they first make the pivot equal to 1, and then they try to do the elimination. And that is just so that if you, it's always nice to deal with the number 1. It basically is better than having something which is, very small or very large as a pivot, right? Because if it is very large, you'll be divided into by 1 divided by, let's say, 1,000,000. That's too small a number. If it is very small, you'll be divided by a very small number and make it very big. So the way Gauss Jordan usually works is you pick the pivot 1 and then you do the second step of elimination. So that was just high level. If you did not quite grasp that, it's done so quickly, I'll solve a problem, and that should help you to understand this. So we'll solve the same problem we did for Gauss elimination, the first one last time, and then we'll try to do it with Gauss Jordan. Okay, so here is the problem. Just in the interest of time, I'm just going to copy the problem. So this is the example we'll solve. It's from the last class. So we'll say use Gauss Jordan elimination. Yes, the first step is to write the augmented matrix. So 2, 1, 1, 7, 1, -3, 1, -2, 2, 2, -1, 3. This is A, this is B. So what we are after is this. Our goal is to reduce this to 1, 0, 0, 0, 1, 0, 0, 0, 1, C1, C2, C3. And if you do it right, then your answers are, for x1, it's going to be C1, x2 will be C2, and x3 will be C3. As simple as that. Okay, so let's work with that. Create a 1 in the pivot, eliminate everything below the pivot, and then keep doing that till you get an identity matrix. Okay, so here we go. This is the first thing you notice is that we want to have 2 as the pivot, but 2 is not equal to 1. We need to make it 1. So we divide the first row by 2. When I say divide the first row, you need to take the entire row. So 2, 1, 1, 7, all those elements have to be divided by 2. So here it is. I like to write it this way, just a shorthand notation, and just to see. So row 1, new row 1 is old row 1 divided by 2. So let's look what it is going to be. It's going to be 2 divided by 2, which is 1. 1 divided by 2, 1 divided by 2, 7 by 2. The 2 came from here. So 1, 0.5, 0.5, and 7 divided by 2, so 3.5. Everything else is untouched. So I write row 2 and row 3 as is. So we have 1, -3, 1, -2, 2, 2, -1, and 3. Okay, now in a good shape to reduce everything below the pivot to 0. As everything below that 1 should be 0. So we can see that can be done as follows. We do row 2 equals the old row 2 minus, it's the same thing as Gauss elimination. 1 divided by the pivot times this 1 times row 2, sorry, row 1. This 1 always goes here. And then this 1 will go here. So it's row 2 minus row 1. The first row is unaffected. The second row, we just do 2 minus 1. So 1 minus 1 is 0. Minus 3 minus 0.5 will be minus 3.5. 1 minus 0.5 will be 0.5. Minus 2 minus 3.5 will be minus 5.5. Okay, and then we can actually do another step instead of trying to rewriting it. So we also need to get rid of this 2. So that'll happen if I do row 3 equals the old row 3 minus, again, the 1 will come down times 2. This is this 2 times row 1. Okay, so row 3 minus 2 times row 1. So 2 minus 2 times 1 is 0. Then we have 2 minus 2 times row 1. 2 minus 2 times 0.5 is 1. So 2 minus 1 is 1. Then we have minus 1 minus 2 times 0.5. So minus 1 minus 2 times 0.5. Minus 1 minus plus, so minus minus plus 1. So I think it's 0. No, my bad. There's no minus here. It's just 0.5. So it's minus 1, so minus 2. So it should be minus 2. Then we have 3 minus 2 times row 1, 3.5. 3 minus 7, minus 4. Okay, so what we've achieved by doing this is 2 zeros. Okay, now let's turn our attention to the second row. We have minus 3.5 over there. That's going to be our pivot. So first thing we do is we reduce that pivot to 1. So we do row 2 is row 2 divided by minus 3.5, 1, 0, 0. The first row is unaffected. The last row is unaffected. Okay, so now we need to do minus 3.5 divided by minus 3.5. That's 1. 0.5 divided by minus 3.5. It's actually minus 0.1428. Then we have here minus 5.5 divided by minus 3.5. This comes out to be 1.5714. This. Zeros here and here. So I ask myself, what can I do with the pivot, which is this one, to get zeros in row 1 and row 3? So you can see that in order to do that, what I need to do is I need to do row 1 equals the old row 1 minus the 1 comes from here times 0.5 row 2. So let me this 0.5 is from there, and this 1 comes from it is. So hopefully you can make the connection now. So if I do that, I'll invariably end up with a 0 in row 1, column 2. Next, in order to get rid of this one, make a 0 over there, what I do is I do row 3 equals row 3 minus, again, this pivot goes down, and then this one will go here times row 2, right? So again, this is the same as here. And then let me show that with a different color. This one went there. So again, if I do the same, what I wrote there, it will essentially reduce to 0. So when I do that, so these operations, and you should do the math yourself. What I got is the following augmented matrix. 1, 0, 0, that row, that column is unaffected. Then I have 0, 1, 0. Then I got 5, 7, 1, 4. Minus 0.1428 minus 1.8572. Then we have 2.7143, 1.5714 minus 5.5714. Okay, so the next step is to create a 1 in row 3, column 3. So I don't want 1.8572. So what I'll do here is take row 3 and divide it by the pivot 1.8572. So when I do that, I get 100,010.5714 unaffected, 2.7143 unaffected, 0.1428 unaffected, 1.5714 doesn't get affected. And then I have a 1 here because I divided by 0.8572. And then I divide 5.5714 by that, I get 3.001. Okay, now the final thing I need to do is create a 0 here and create a 0 over here. So in order to do that, I use the pivot, which is this one. This is how I do it. I need to work with row 1. We old row 1 minus this pivot goes down, 0.5714 goes up, and I do that times row 2. Sorry, row 3. Pivot. And finally, row 2 equals the old row 2 minus the pivot goes down, minus 1.428 goes up, times row 3. Okay, so I just put down the answer. It comes out to be 100,010. The first two columns remain unaffected. I get 001 because of these operations. And then I have 1.0001, 1.998, 0.001. So now I have it in the form I wanted. This is the identity matrix. This is that C1, C2, C3. So the answer is x1 is 1.0001, x2 equals 1.9998, x3 equals 3.001. Okay, actual answers are x1 is 1, x2 is 2, x3 is 3. Okay, so now question for you. Why did I end up getting 1.0001 or 1.998? Why didn't I get x2 equals 2? Yeah.
One possible reason I could think of would be that you have not enough numbers after the parenthesis. That could be a reason.
After the decimal, you mean?
Yeah.
Yeah. So if you do this calculation with that's actually the correct answer. So what he said was I don't have enough decimal places, any more significant numbers after the decimal places, and that's the right answer. So if you do it with
fractions, right?
Fractions. So if you do no, not fractions, but the numbers after decimal places, I've carried out 4 decimal places, right? So what happens? Every calculations, I lose accuracy. Anything after those 4 decimal places is lost. So they could be like 9999. If I had kept them, they could actually have rounded up to 2.000, right? So because I'm dealing with 4 number accuracy everywhere, all my calculations, I just keep losing accuracy. If you do this with a computer like Octave or MATLAB, it actually preserves accuracy to 13 decimal places. So you will not end up with this problem. You probably get 1, maybe you get 1.0000, and there'll be a 1 in the 12th decimal place, something like that. But you'll see it's sufficiently, the error is not as big as it is now. Now you may say, who cares? 1.998 and 2.000 are about the same thing, and I don't care. Now that might be true for the specific application I'm dealing here, but in a different scenario, it could be incorrect. So for example, if you're trying to compute the distance from here to, say, the moon, and it boils down to solving equations like these, and you just carry over 3 decimal places, and you'll end up with an answer which is off by 1,000 kilometers or 100,000 kilometers, right? So the units really matter, and that's where you'll have to worry about accuracy up to maybe 13 places. So there are applications where you don't care, and some applications you do care. So it really is specific to your application. Given a choice, try to keep everything to 13 decimal places. Okay, any questions on this? Okay, so let's go to the fun part, which is trying to write computer code to get this going. And here, this is one of the problems where I would just surrender to ChatGPT because it's much easier for it to figure out a code for this. So what I'll do here is go with my earlier chat. So this chat was on Gauss elimination. So really up to you if you want to keep that chat, but I would just make a new chat for Gauss Jordan elimination. Yes, I'll literally tell it what problem needs to be solved and see if it can generate the code for it. So solve using Gauss Jordan in Octave. And then the problem is 2x1 plus x2 plus 3 equals 7, x1 minus 3x2 plus x3 equals minus 2, and then 2x1 plus 2x2 minus x3 equals 3. Okay. Okay, so what it did here was there apparently is a function available in Octave which does it for you. So I'm curious. I've not seen this before. I tried it this same on a different in a different login. It actually gave me a different answer. Let's try this out. Seems interesting. So let's go here. Okay, and Control S. Books, lectures, Gauss Jordan. So let's call it main built-in.m. It's just saying it's built-in command. So I think I just happened to run this code. So what it does here is this command rref actually reduces to this row echelon form. That's what it's called. And then you can actually read off the answer. It's 1, 2, and 3. Okay, so that's one way of doing it. Let's see if it can generate the code for me. Solve, write a function Gauss Jordan without using RRF. Okay, so here's the code. Okay. Yes. Okay, so what it did here is wrote a generic function which basically takes the matrix A and then reduces to, well, solves the problem, but it expects the input to be uh, the augmented matrix. You can see this is an augmented matrix, 3 cross 3 rows, 4 columns. Now, I could make it write a function which exactly what I want. I actually wanted to take inputs as A and B and produce the output. It actually uses the augmented matrix. So what we can do is we can just do it ourselves instead of trying to make it do it. So what I'm going to do is just copy this. Let's make a new function for this. Okay, and then what I'll do is I'll actually have 2 inputs. I don't want 1 input. And then A equals A, B. So I just augmented the matrix. Okay, and Gauss Jordan looks right. Let's go back to the main function which calls it. The new ones. Okay, so what I want to do is I would rather call it as B. So 7 minus 2, 3. And then I just don't want it to be like so. And then my input should be, I think it's A comma B, okay? Let's call that main Gauss Jordan. Okay, let's see what happens if you run this. Undefined near line 1, column 2. It's usually a problem when I write something new. I'm going to close this. This is an Octave glitch. I think it'll go away once I try to uh, open this again and do the change directory. Let's hope it gets fixed. Okay, so let's run this. Okay, that's not right answer. 0, 0, 1. So I'm just checking my equation. It looks right to me. 7 minus 2, 3. Okay, what went wrong? Maybe I should. I think it might be just that I redefined it. Okay. Huh. It's a different answer. 0.5. Okay. Anybody see the issue anywhere? Oh, here it is. I should have fixed everything. My bad. Okay, let's see if it works. 0, 0, 1. Okay, now that we have access to our own solution, let's check if everything here makes sense. Okay, so this is going to make it print the augmented matrix at every iteration. There's a slight difference from the way it's doing it. It's actually maybe not. Let's see the output now. It's clipping the output. Oh, there it is. Oh, I see. So if you look at the solution A augmented, this is the result produced at the end. A augmented, it's exactly what it is. But the problem seems to be not this, it's just what is sent out. So this needs to be fixed. So what it's doing is sending in, the issue is that it's the output X which is messed up. It's not the A augmented. So if you see this code, what is columns? Columns is it's going to be the columns of A. So there are 3 rows, 3 columns. So it's taking the third column and padding it as X and sending it out. So third column is 0, 0, 1, and that's what it's sending. So the fix to this is actually, I should have. Okay, so I think I need to change this slightly and to augment it first. Okay. Now we'll have 3, 4 because I augmented as 3 rows, 4 columns, and then the last column is what we need. So now let's run this. And you see it's case 1, 2, 3. That's the right answer. And then you can also check the solution progress. So this is not printing. This is like a Windows bug. It doesn't print the output the way I want it to print. So what I can do is this. Let's go here and just say diary output.txt, and then we can do diary off on this, and now it produces the output in Gauss Jordan. Here it is. Okay, so we can actually check our answers. That is what we wrote by hand with this. So the augmented is what we start with. Then what's doing is it basically divided the first row by 1. So you got 0, 1, 0.515. But then you see that there's a slight difference here. It's so this is my bad. So this actually did both steps. It combined the way I printed it. It combined both steps. It first divided by 2 and then did the 1, 0, 0. So in order to fix that, let's delete this. I can actually print the output the right place. So I need one more A augmented to be printed. So if you could go here, and then so let's see. So here's what it's doing. It's basically augmenting it. We saw what that is. Forward elimination. This basically normalizes to get a pivot equal to 1. So I should print this. Then what it does is does the elimination to make zeros. So I have to print that. Okay, now it should work fine. And I can compare this with against my answer. So if you look at output.txt, A augmented is here. So we have yeah, two. So one. So here is the first start, and then if you see here, what it did was it took the first row and then divided it by 2. So you got 1, 0 0.5, 0 0.5, and 3.5. Then it basically eliminated this 1 and 2 using this 1 as a pivot. So you get this, and you can check this against the answer I got. Then what it did was it took divided by minus 3.5 to change this pivot to 1. And then it used this pivot to create 0, 0. And then finally, it created this 1 over here by using negative 1.857 as a pivot. And then finally, it eliminated these two, and then you got this matrix. Now you can see the difference. Here it actually got 3.000, while I got 3.001. That's because I kept only 4 significant places. And the code here, Octave, actually maintained 3 places accuracy. So that actually worked fine on a machine which has high precision. Okay, so this is fine. The problem with this code is going to be the same as the one which we witnessed earlier for Gauss elimination. That is, if one of the pivot is 0, it's going to be a problem, right? If you run this, you get NaN, not a number. You get infinity because the pivot is 0. When you divide it by the pivot, you get infinity. So the way to fix this is to go to say ChatGPT, and you know what? Since I modified the code, telling it to improve on the existing code will give me the same code with, and I have to do modifications again. So what I'll do is I just take this code which I have, which is Gauss Jordan, and I'll tell it to do partial pivoting, which is what we did for Gauss elimination. So go here and say, please add. Now it's not a human, so you don't really need to put please. Add partial pivoting to this Gauss Jordan code. If you want to, if you just press enter here, it'll actually take that as an input. But the way to write more lines of code below and then send it is to do shift enter. So if you do shift enter, it goes to the new line. Then I'm going to do another shift enter. So shift enter, new line, control V, the same code I wrote down. And now I can do enter and go in, or I can just do this. So let me just do enter. So now what it did was it took that same code I wrote, but added some stuff for partial pivot. In fact, it's over here. Okay, so let's take this code, and then we just switch our code with that code. Okay. Now, if I run this with 0, well, I could also check it, right? So how would I check it? Well, I could do this A, right? This is how you can do it without using Gauss Jordan, just A/B, which is the same as inverse B. So let's run this. Okay, this doesn't look right. Oh, okay, I know what happened. It printed both solutions one after the other, so it looks like 6 rows, but it's really 2 solutions. Okay, so the first one, 1.1818, 2.5454, 4.4545 comes from A/B. Then there's the space. This basically creates a new line, creates an empty space or empty line, and then this is the one which is produced by solution. Okay, so you can see they match. Okay, so this is good, and your code is kind of robust to pivot being 0. Let's check this. Yeah. Oh, this was supposed to be 2, I think. Yeah. You're back to 1, 2, 3. Okay, questions?